In Chapter 3, we classified matter as pure substances or mixtures. Mixtures can be homogeneous or heterogeneous. Before you proceed, define the terms matter, mixture, and homogeneous mixture. In addition to homogeneous and heterogeneous, mixtures can also be classified as solutions, colloids, and suspensions based on particle size, particle settling, and particle separation. Solutions have small particles which don't settle and can be separated by physical barriers. Colloids have intermediate particles which don't settle and can be trapped by some physical barriers called semi-permeable membranes. Suspensions are heterogeneous mixtures with large particles that both settle and can be separated by filters. Here are some common colloids. Note that sometimes colloids are hard to distinguish from solutions without the help of a microscope. In general, solutions are clear while colloids are opaque. We will refer back to solutions, colloids, and suspensions later in the chapter. For now, let's take a closer look at homogeneous mixtures, called solutions. You need to be able to identify the two parts of a solution, the solute and the solvent. Also, you need to describe how a solution is formed. A solute is a substance that is being dissolved by another substance, which is called the solvent. Solutes can be liquids, gases, or solids. Examples are ethanol, a liquid solute in alcoholic beverages, carbon dioxide, a gaseous solute in Coke products, and sugar, a solid solute in sugary drinks. Since solutions are homogeneous mixtures, the solute is evenly distributed throughout the solution. Also, you cannot separate the components by filtration, as both the solute and the solvent will pass through the filter paper. For a solution to form, solid particles dissolve in the solvent until they are uniformly distributed. In this example, copper sulfate is a solid solute, and it will be evenly distributed in water until the entire solution is blue. Here are some examples of solutions. Note that the solute is present in smaller quantities and the solvent is present in larger quantities. One of the most common solvents is water. Pause the video and describe the shape, polarity, and forces that hold water molecules together. The three atoms of water have a bent geometry, and oxygen and hydrogen covalent bonds are polar, and they don't cancel in the molecule, so water is polar. Water is held by special type of dipole-dipole interactions called hydrogen bonds. For a solution to form, the interactions between a solute and solvent must be stronger than that of the solute-solute or solvent-solvent interactions. In general, if the solute and the solvent have similar polarities, then the solute-solvent interactions will be strong and solutions will form. A simple rule to remember is like dissolves like, which means polar solutes will dissolve in polar solvents, while non-polar solutes will dissolve in non-polar solvents. Ionic compounds can also dissolve in water. For example, sodium chloride will undergo hydration as water molecules pull the sodium and chloride ions apart. Since water is polar, the resulting interactions are ion-dipole interactions. As we discussed before, an ionic compound will dissolve if the ion-dipole interactions are stronger than the ionic bonds in the ionic compound and the hydrogen bonds in water. For polar solutes, since like dissolves like, they will dissolve in polar solvents such as water. Recall what hydrogen bonding is. Solutes can be further classified as electrolytes or non-electrolytes. Electrolytes, as the term suggests, form solutions that conduct electricity. This means that they dissolve and dissociate into positive and negative ions, which can transmit electricity. A strong electrolyte will dissociate completely into its respective ions. An example is sodium chloride. Strong electrolytes give solutions that are very good conductors of electricity. Weak electrolytes partially dissociate in water, forming a small amount of ions, while the rest remain as intact undissociated molecules. An example is hydrogen fluoride, which produces a small amount of H+ and F- ions and is a weak electrical conductor. Non-electrolytes do not dissociate at all, and the solution contains only molecules, so it does not conduct electricity. One example is methanol. To quantify how well a solute dissolves in a solvent, we use the term solubility. By definition, solubility is the maximum amount of solute that dissolves in 100 grams of a solvent. As you slowly add a solute to a solvent, at first the amount of solute is less than the maximum amount a solvent can hold. The resulting solution is unsaturated. If you continue adding the solute, you will reach the maximum amount of solute a solvent can hold. The solution is now saturated. The rate of dissolving equals the rate of recrystallization, which is when a solute comes out of solution. If you add more solute to a saturated solution, the rate of recrystallization is greater than the dissolution, so the solid will remain undissolved. There are a few factors that affect solubility. One is temperature. Imagine trying to dissolve sugar in iced tea compared to hot tea. The sugar will dissolve faster in hot tea because temperature increases the solubility of solids. For gases, it's the reverse. A closed Coke container left in the sun will pressurize because the dissolved carbon dioxide will escape the liquid as temperature increases. So for gases, increasing temperature decreases solubility. Pressure also affects solubility. Using a Coke can as an example, when it's closed, the pressure is high, so more carbon dioxide is dissolved in the Coke. As soon as you open the can, the pressure decreases, and so does the solubility, so the carbon dioxide will escape as a gas. The nature of ionic compounds also affects solubility. We mentioned that a solution will form if the ion-dipole interactions overcome the ionic bonds in the ionic compound and the hydrogen bonds in water. To determine if an ionic compound will dissolve in water, we use solubility rules. In general, ionic compounds will be soluble if they contain at least one of the ions shown in this table. Note that this table will be provided for you, so you don't need to memorize it. Just learn how to use the table as a resource. Here are some examples of ionic compounds for you to practice solubility rules. Use the solubility rules in the previous slide to determine the relevant rule and determine the solubility from that rule. So we have looked at solutes and solvents, the components of a solution. We defined solubility and saturation, and we further classified solutes as electrolytes and non-electrolytes. Next, we will describe a solution by its concentration, the amount of a solute in a given solution. As always, happy studying.